Thank you, everyone, and welcome to this new webinar. Let me share my screen. Okay. So this new webinar is about some new tools that we implemented regarding the constraint handler part of the analysis. And on the first half of the webinar, I will discuss the new constraint handler that we implemented, which is the automatic constraint handler. And then in the second part, I will show you a new feature that now all the constraint handler in OpenSees have, which is the ability to treat constraints incrementally. So basically, a constraint imposes exactly a constraint on the displacement. And if a constraint is applied not only at the beginning, but on a later stage of the analysis, now in the current version of OpenSees, this constraint will apply the constraint incrementally, so only on the incremental part of the solution. And this actually allows us to do many things, for example, construction stage analysis. Okay. So by tomorrow, you will see, we will share on our website both the recordings, because now it cannot be on YouTube, but also 3 files that I will show you today. So the first one is called Model 01 Overlapping MP Constraints. And in this example, I will show you what are the benefits of using the new constraint handler that we developed. And in the second part of the webinar, I will show you 2 different models. And this one instead will explain you how all the constraint handler now can apply constraints incrementally and how you can use them. Okay. So first of all, before starting, I just want you to I want to show you the documentation of the new constraint handler. And by the way, since this one has been added in the latest version of OpenSees, it is available from version 3.7 on. So if you use a previous version, this new constraint handler is not available. And same happens for the documentation. So if you go on the old documentation wiki of OpenSees, you will not be able to find it. But if you go on the new documentation, which is on the GitHub pages here, you just type OpenSees GitHub on Chrome and you will find OpenSees documentation. You go on Command Manual, Analysis, and under Constraints, you will see that now you have the old 4 constraints that are very well known in OpenSees, and you have another one, which is called Auto Constraint Handler. Yeah, I think there is someone with the mic open. Okay. So this one is the one that we implemented recently, and it's called Automatic Constraint Handler. Now I will briefly explain you the inputs, and then I will tell you how it works. Now, by default, you can just type constraint auto, and these other ones are optional, so you are not forced to use them. Okay, you can use them to set up some default values. Now, the first one is verbose. So if you apply this option, you will just get some debug messages that will explain you how the constraints are being applied, and I will show you later on. And then there are 2 other options for the penalty approach. So what this constraint is actually doing is that it is a mix of the transformation constraint handler and the penalty constraint handler. And it will apply the transformation constraint handler for single point constraints and the penalty constraint handler for multi-point constraints. Now, what is the advantages of this? I will show you in the first example. So I will open now the first file, which is Model 01 Overlapping MP Constraints. This is a very simple model. I just want you, I wanted to show you what can be a common problem in OpenSees when you use transformation constraint handler and how you can solve these kind of problems. I've been talking about this topic in many webinars, okay? But now there is this new constraint handler, which makes it even easier. So what is the problem of constraint handler in OpenSees? By default, OpenSees uses in any analysis, and let me go to the default settings. By default in OpenSees, this one is the is the constraint handler that you have, which is the transformation method. The transformation method basically transforms the system of equation, removing the constraint equation for single point constraint, or transforming the constraint equation in favor of the retained equation when you have multi-point constraints. The main advantage of the transformation method is that it applies the constraint exactly, but there is a problem. When you have overlapping constraints, which means when you have a node which is a retained node in a constraint, and at the same time is a constraint node in another constraint, the transformation handler is not able to enforce both constraints at the same time. So one of them will be skipped, and unfortunately in OpenSees, OpenSees doesn't report that one of these two constraints have been skipped. So the problem is that you will see that you will see no error, but the analysis will not give you the expected results. Okay. So what I'm going to do now is to show you an example where the transformation handler fails. Okay. So when you will download the file will already have the automatic constraint handler. But now to show you the failure, I will go with the default one, which is the transformation. Okay. Now, just before running the analysis, I will explain you a little bit what is this file. It's very simple. Let me hide this interaction. Okay. So in the geometry, you have 3 different geometries. This is a very simple schematic one floor structure. And you have a compound geometries made of 4 edges for the 4 columns and 4 beams. Now I designed them on purpose with a distance between beams and columns, just because I want to show you the connection between beams and columns. And then you have a reference point for the rigid diaphragm. Okay. Now imagining this model, for some reason you want to create a connection which is not continuous between columns and beams. For example, if you have a steel structure and you want to represent some sort of joints here, or simply if you want to create beam end releases, or if you want to put nonlinear hinges in between. So whenever you don't want a continuity between a beam and a column, you will typically model them separately, and then you will apply a sort of interaction between them. Okay. Now, in this specific example, what I wanted to do is that I wanted to release the out-of-plane rotations of all the beams, okay? So as if all the beams are hinged. But at the same time, I want to apply a rigid diaphragm, okay? So what I did is that I modeled columns and beams separately. Then I have 3 different interactions, okay? So let me show them. Let me show you all of them. So the first one is the interaction for the rigid diaphragm, okay, which is this one here. And if I edit it, you will see that the master node is the reference point in the middle. And the slave nodes are the top vertices of the columns and all the edges of the floor beams, okay? Now what happens? At the same time, I need 2 other interactions because I want to connect the translational and torsional degrees of freedom of the column, of the beam, sorry, with the top of the column. And I want to release the out-of-plane bending rotations. So in order to do that, I need to create other 2 interactions, okay? So one is called the joint along the X direction, where the master are the top nodes, you can see them here, are the top nodes of the columns, and the slave are the nodes on the floor beams. Okay, this one is for the X direction. Then I will explain you why I kept the interaction separated from X and Y. And I did the same for the Y direction, which are these other 4 here. Also in this case, the master is the top of the column, and the slave are the end nodes of the 2 beams in the Y direction. Okay, so these are just the 3 interactions. Now, regarding properties, I don't really care about this model, so it's just one single elastic section made of elastic concrete. I'm using here kilonewton meters, but don't look at the material properties. This is just a numerical example, okay? So same cross-section, same material models for both columns and beams, and same finite element, okay? So a three-dimensional 3D elastic beam column. Then regarding boundary conditions, I have a fixity at the bottom, okay, in all degrees of freedom. Then, as you already know, whenever you have an extra node as a reference for a floor, this node will be connected to the slave nodes of the floor with the rigid diaphragm. But the rigid diaphragm only handles the in-plane displacement and in-plane rotation. So these 3 degrees of freedom are not connected through the rigid diaphragm, so you need to fix them. Okay, otherwise you will have a singularity on this node. So this is pretty standard in OpenSees. So these are the only 2 single point constraints that I need: fixity at the bottom and the fixity of the 3 extra degrees of freedom for the floor diaphragm. Then I have a set of multi-point constraints. Okay, so the first one is the rigid diaphragm, which is imposed on this interaction. Perpendicular direction is 3 because I want to apply it on the XY plane. And then I have the equal DOFs for accounting for the beam end releases. Okay, so for example, in the X direction, I want to connect the translational degrees of freedom of the end nodes of the beam and the top node of the column. And I also want to connect the torsional degrees of freedom. So for the beams in the X direction is the rotation about the global X direction. Okay, so these 2 instead are free. And I do the same for the joint in the Y direction. But in this case, the torsional degree of freedom will be about the global Y axis. And this is the reason why I had to create 2 different interactions, because in OpenSees, multi-point constraints are defined with respect to the global coordinates. And one extra thing is the mass. Okay, so in this case, I assigned only masses in the X and Y direction. I didn't need to put it in the Z direction just because I wanted to show you only the 2 translational and 1 torsional modes of vibration. I will use the eigenvalue analysis to show you the singularity of the problem. Okay, so you only have this distributed mass. Keep in mind that in OpenSees, when you assign distributed masses on frames, it should be a mass density times an area, so times the cross-sectional area. So in this case, it was 2.5 times the area, which is 0.25 here. Okay, so regarding the analysis, instead, I create a simple MPCO recorder where I only record the modes of vibration, okay? Then I apply the constraints, and I apply all of them. So fix it at the bottom, fix it at the reference point of the floor diaphragm, and the 3 multi-point constraints: rigid diaphragm, joint X, and joint Y. Now, as you can see here, the main issue is that I have some, for example, imagine this node on top of the beam, right? Sorry, on top of the column. The node at the top of the column is a master node in this degree of freedom, in this multi-point constraint, but at the same time, it is a slave of this other master node here. That's why I call this example overlapping constraint. This is very typical, but this usually leads to issues in OpenSees if you use the transformation handler, because the transformation handler is not able to apply this kind of overlapping multi-point constraints. And well, of course, there is also another issue for this node here, because this node is slave in one equation, but is also slave in another equation. So the transformation handler is not able to handle this overlapping kind of constraint. Okay, so after this, I set up the eigenvalue analysis. I explained this topic many times in our webinars. The point is that when you want to do an eigenvalue analysis, if you do not put the analysis settings before, the eigenvalue analysis will create default settings, okay? And default settings are transformation, RCM number, and by default, it uses the profile SPD. So the reason why I typically set up the analysis before is because, for example, when you're doing an eigenvalue analysis of a huge model, you either don't want to use the transformation method for many reasons, for example, as in this example here, but many other times you don't want to use a profile SPD solver because sometimes you have a problem which is not symmetric and positive definite, or in general you have a huge model, so you may want to use one of the sparse solvers like the UMF pack. But anyway, we'll start with the default now, with the default settings. Keep in mind that in STKO, if you want to set up an analysis for an eigenvalue analysis, you can simply create an analysis step here. You set your components as you wish, and then instead of running the analysis, you just set the duration and the number of increment equal to 0. So STKO will not run an analysis, but will simply write the settings, okay? In such a way that the eigenvalue analysis that comes after will use these settings. Keep in mind that if you do this, you don't have to use wipe analysis, because wipe analysis in OpenSees is a command that is actually used to clean the settings of the analysis. But I don't want to do it here because my main intention is to use these settings for the eigenvalue analysis. Okay. Okay, so now I will start with the defaults. So transformation and profile SPD. So, and then I run a simple eigenvalue analysis. I'm requesting for just 3 eigenvalues. And then I want to print the model properties. And finally, a simple record, because as you know, in OpenSees, the eigenvalue analysis does not trigger the record command on the recorders, so you have to do it manually. Okay, so if you, well, then I mesh the model, but I mesh them with a simple one element per member. Okay, so this one is my meshed model. So if you look at a model like this, it seems that everything is correct because I set up all the constraints correctly, all the multi-point constraints correctly. But if I run the analysis, you will see that I have a warning. The UMF pack is telling me that there is a numerical analysis error. And this one is the typical error of the UMF pack that says that the model is singular, okay? So if I go back here in setup analysis, and I use another solver, for example, the profile SPD, you will see something similar. Of course, the error will be different, okay? But the concept is the same. So a UMF pack does a numerical pre-computation and tells you that the system is singular, so cannot be factorized. The profile SPD tells you in what degrees of freedom, so what are the equations where the diagonal is 0. Anyway, the concept is the same. It is telling me that some degree of freedom is unconstrained, okay? Now, the point is that I set up everything correctly, so what is the problem? The problem is that with the transformation method, the rigid diaphragm is not applied correctly before, or actually the other, the second one that I put in the constraint. Let me see. Okay, so the rigid diaphragm comes first. So the rigid diaphragm is applied correctly, but the beam end releases between the beams and the columns is not applied correctly because when the transformation tries to apply this constraint, it finds that the slave node and the master node in this constraint is already used in this other constraint. So it's not able to transform the system of equation anymore. So a typical solution that you had before version 3.7 in OpenSees was to use the penalty approach, okay? So now let's go to penalty and let's see if it solves the problem. So I go to setup analysis and I go to penalty. Now by default, penalty starts with a value which is 1 to the power of 18, okay? Then I will show you what is the problem of the penalty one. But let's start with this value, which is the default. And let's see if the analysis runs fine. Okay, so now the analysis runs. So as you can see, there is not a problem of singularity. Simply by changing the constraint handler, now I'm able to solve the problem, okay? So I obtain my 2 and 3 periods, and I go here in post-processing, and I check that everything is correct. So I go here, surface color map, and I want to see the modes of vibration, both here in deformation. And I can see the first mode, translational in Y, and then I have a rotational mode, okay? So this is standard. Now, what is the problem with penalty? So penalty has the advantage that it is able to solve overlapping multi-point constraints because it does not transform the system of equation. It just adds very stiff elements, okay? So imagine that all these constraints in the penalty handler, they are replaced with very stiff elements that connect the degrees of freedom involved in the constraint. So if you have overlapping constraint, you just have overlapping stiff elements, but this is not a problem. The only problem that you have with the penalty constraint handler is that you should be able to set up these two parameters, okay? Now, by default in STKO, we start with 1 to the power of 18, but since this one is an absolute value, is not a value that is valid for any kind of problem. So for example, how do you calibrate the penalty parameter for a given model? So let me start a Python GUI. Okay, so in my model, in this example, I have a Young modulus of 3 to the power of 7, which because I'm modeling in kilonewton and meters. So this one is the Young modulus of my, well, the only Young modulus present in my model. The area in my model is 0.5 times 0.5, as you can see here in the cross section. That's not here, sorry, it's here. 0.5 times 0.5. And the typical length of the finite element is, now let's take, for example, the column is 5 meters, okay? So that now my typical stiffness is AI over L, which is this value here. Now, for doing this calculation, don't care about an exact value. Here, I just want to know what is the order of magnitude of the stiffness in my model, because keep in mind that in a very complex model, you don't have only one material, you don't have only one area. Also, the finite elements may have different sizes. So just pick the stiffer of them and compute your typical stiffness. Once you have your typical stiffness, you may want to compute the order of magnitude, okay? And the order of magnitude is defined as an integer, so you can round the log 10 of this typical stiffness, okay? So if you look at the order of magnitude, is 6, okay? Now, you know that in computers, when you have to deal with floating point numbers, they have a finite precision. Now, in OpenSees, we use double precision floating point, and they have 16 significant digits. Now, what it means is that if I apply in a system of equation, in a stiffness matrix, for example, if I have one number that is higher, that is larger, more than, let's say, 16 order of magnitudes with respect to another number, the smaller number will be considered as 0, okay? So typically what we do is that the maximum penalty value that I want to apply to this one should be 10 to the power of the order of magnitude plus 8. Why 8? Because 8 is exactly 1/2 of the 16 significant digit of a double precision floating point number. This basically means that if I apply a penalty stiffness, which is 10 to the power of 14, I am in between the application of an exact constraint and the numerical precision, okay? So the smaller is this number, the more accurate is the stiffness matrix, but the less accurate is the imposition of the constraint, okay? So you may want to play with that. Just to explain you what it means, let me start with an optimal value, let's say 1 to the power of 14. So here I'm in between the correctness of the constraint, which will be obtained only with an infinite value, But if I use an infinite value, my system will be singular. So I have to be in the middle. That's why I choose +8 here. Okay, so if I do an analysis with this one, you will see that pretty much the results are the same as before. Let's say are somehow correct. Okay. Now let's see what happens instead if I use a very huge number, because this is the danger of penalty, that you may use very huge numbers. Okay. So let's say I do order of magnitude +16, which is the limit for my numerical stability. So let's try to put 10 to the power of 22 here. Let's see what happens. Now you see that the mass participation factor completely changed. But if you look at the periods, they are completely gone, basically. They say that there is a period of 9 seconds. But most importantly, you are seeing once again the instability here. Because now, as I told you, now you have some numbers in your stiffness matrix which are very huge, and all the other numbers are close to zero in terms of how the computer treats the floating point precision. The other numbers, for example, the typical stiffness of my beams and columns, are basically zero for the computer. So the SPD solver is telling me that there are many degrees of freedom which are zero. Okay, so if I go here in the post-processor and try to reload this one, you can see that the results make no sense at all. Okay, so this one is one problem with the penalty method. You may use values which are too high. The other problem is what happens if my value is very small. So for example, imagine I assign a value which is smaller than the typical stiffness, okay? So the typical stiffness is 1 to the power of 6, 10 to the power of 6. Let's put 10 to the power of 3. So let's put 1000. So now the stiffness that the system will use to impose the constraint will be even smaller than the stiffness of my structure. Now here the problem will be the opposite. So the system will not be singular. As you can see here, I don't have any singularity. My period is still wrong, but for another reason. So let's try to see now what is the problem. Now it seems pretty much correct. If I go here and look at the other modes, they seem correct, but I want to show you something, what really happened in this case. Look at this node. This node should be fixed, but as you can see, it is displacing. And if I try to displace with scale factor, let me put something more. Okay, so here I'm at the end of the mode. When I'm doing the deformation, you will see that the node that should stay at 0 is actually moving. Okay, because now the stiffness, the penalty stiffness that is down here, now imagine the penalty is like placing very high stiffnesses on the degrees of freedom which are constrained. But now I use a very small number, so this stiffness is not really stiff. So it displays together with the structure, okay? And if I make it even smaller, you will see that it displays even more. So let's exaggerate here. Okay, now the period increases, of course. And if I reload this one, okay, you will see that the node here is displacing even more. Okay. So now, as you can see, the problem with the penalty, well, penalty has both an advantage and a disadvantage. Okay, so it can solve any kind of constraint, but the real problem is that you should be able to calibrate perfectly the degrees of freedom that you want. And a lot of people do not know how to do this stuff. Okay, or it can be annoying because now it's easy because I have a very simple model, but the user don't want to compute these factors every time in every analysis they do. So what we decided to do was to implement a new constraint handler, which is the automatic one. And as I told you, the automatic one applies transformation on the single point constraint. So in these points, the constraint is applied correctly. And regarding the multi-point constraint, they are applied with the penalty method but we used an automation to make it automatic. So what I'm doing here is that instead of computing a user-defined penalty stiffness, do it automatically. So OpenSees will find for each multi-point constraint what is the typical stiffness in the nodes involved in that constraint, and we'll put a penalty value locally here, which is, for example, in this case, 1,000 times more, so 3 orders of magnitudes more than the stiffness that is here, okay? So in this way, you're playing with a relative value, which will be always fine, okay? So you don't have to care about what is the stiffness of your model, because whatever the stiffness is, OpenSees computes the stiffness, increases the value by this factor that you decide, but 3 is a reasonable number. So basically, the rigid diaphragm and the connection for the beam end releases will be 1,000 times stiffer than the other elements, okay? So very easy to use. You simply set up that, you run the analysis, and you will obtain correct value. As you can see here now, the values are very correct. You have 100% of the excited mass in the directions here, and you have a very, very small error due to the penalty there, but it's really small, okay? So the concept is that simply using the automatic handler, you don't have to care about the value that you assign to the penalty parameters, okay? So this makes the analysis much easier to handle, okay? So as you can see now, the node is not displacing anymore on the bottom, okay? Okay, so this one is about the first part of the webinar. Then if you have questions about this topic, you can write them in the chat and I will try to answer later on. Okay, so this one is about the new constraint handler that is the one that basically I use every time now because it combines the efficiency of the transformation for the single point constraint and the robustness of the penalty method for the multi-point constraint. Plus, you don't have to calibrate penalty parameters because it's relative to the stiffness that is in that location. So much easier, much more convenient. Now, a second thing that we implemented in OpenSees is that the constraints now can be treated incrementally, because before in OpenSees there was not a consensus between the different kind of constraints. So if you apply a constraint on a second stage of the analysis, some constraint handler were applying the constraints incrementally and some other were applying the constraint globally, okay? So what we decided to do is to make them consistent with each other. So now all constraints handler will apply the constraint incrementally. And this can be beneficial for example, for construction stage analysis, okay? And I will show you how it works with the second example. So if you go here, model 2 incremental constraint, this one is a very simple example. Here I create a simple wall. I on purpose assigned 2 different properties, a stiffer property on the 2 sides and a softer property here in the middle. You will see later on why, but just because I want to show you better the initial deformation and how this initial deformation is kept into the second stage of the analysis, okay? So here you have a simple wall made of 2 materials, okay? One here and the other in the middle, which is 1/2 the stiffness of the side one. One element, a shell element, a simple elastic model. Then we have fixity at the base in all the degrees of freedom. We have a vertical distributed forces for the first stage. Then what I want to do basically here is I want to apply in a first stage a vertical displacement. Then my top edge will displace of a factor that I don't know a priori. And in a second stage, I want to fix the top displacement at the current location. Now, the problem is that in the previous versions of OpenSees, if I was using fixity in this way, OpenSees will try to bring back the nodes to a displacement of 0. So it will not try to keep the current displacement. But now from version 7 on, the displacement will be incrementally. So if I apply a fixity on a second stage of the analysis, the fixity applies only to the incremental part of the displacement, okay? So if I do something like this, I apply a fixity, and then I apply a push on the top part of the wall, and I set up my analysis in this way. So I set up a recorder, I apply the fixity at the base first, then I apply a vertical load with a linear time series. Then I run my analysis for the vertical load. I keep the vertical load constant. I reset the time to 0. And then I fix the top, okay? So here I'm fixing the top at a displacement of 0, but it actually will not bring back the nodes to 0. It will keep them to the current displacement. And after that, I can apply an horizontal displacement and run the analysis of an horizontal displacement, okay? So this one will be very easy. I'll try to run the analysis. Okay, so first step and second step. And if I go here, okay, let me go in the front position. Let me apply the deformation of 1. And let's go back here. So in the first stage, I'm running 10 steps. This one is going down. The reason why I assigned a softer material in the middle is that because I wanted to emphasize the deformed shape here. Now, at the second stage, I applied a fixity on the top, but as you can see now, the vertical displacement is being kept fixed, but is not going back to 0. So this is very efficient, for example, to keep a displacement at a position which is unknown a priori, okay? But in order to do this, you need to have OpenSees version 3.7, because if you do the same example with a previous version of OpenSees, you will see that in the second stage, my wall goes back to 0 and then starts moving, okay? And that is not correct. So with version 3.7, you will be able to do this one. This concept can be used also with multi-point constraints to do construction stage analysis. Now, if you are familiar with construction stage analysis, especially on soil elements, so with solid elements, there is one problem. In solid elements, you can use the initial state analysis wrapper, and that is typically used, for example, when you create the model of the soil, you run an initial elastic analysis to set up the initial stress due to gravity. Then you bring back the displacement to 0, but you keep the stress state as it is. And then on top of that, you can build your structural model. The problem with the initial state analysis is that it can be used only once in your analysis. It cannot be used multiple times. So imagine you want to create, you want to simulate the different layer of soil being put one after the other. That one will not, you cannot do that process with initial state analysis wrapper in OpenSees. But now with the new constraints, you can apply the concepts of the incremental feature of this constraint to have the same output, basically. Now I will explain you this example with the third case here, which is incremental constraint C stage, where this one stands for construction stage. Okay, so this one is an example very similar to the example before. I just want to show you what it is. So same geometry. I just duplicated the geometry, and let me move it a little bit to show you the interaction in between them. Okay, then I will bring this back to the initial position. So what I have now, I have two stages. Let's say this one is the first wall, and I do an analysis. This wall deforms due to a certain weight. And then in a second stage, I will build another piece of wall on top of that one on the deformed configuration. Now, the problem is that when you build your CAD model, you don't know what will be the deformed configuration. So you are actually modeling this one in the undeformed configuration, okay? So one option now to do this kind of construction stage analysis is to use the incremental features of the constraint, because now if you know that constraints will be applied incrementally, you can think of running an analysis with the entire structure at the same time. This one can be fixed in space, so without any load. This one will displace. Then I will remove the constraints on the second stage, and I will attach this to the second one with an equal DOF. In this way, I will constrain the relative displacement to be equal to 0. Okay, so let me explain you very easily how it works. So imagine you want to construct this wall on top of this other in a second stage of the analysis. Okay, so you create the two walls, you create an interaction between them, and I called it link stage 1 to stage 2. Then, as usual, I have a linear time series. I have the two materials that I showed you before, one element property, and then the boundary conditions. I have here a fixed at the base. Well, let me go back here, which is even easier. Fix it at the base for the first stage. Then I have a fix on the entire second stage model, okay? This entire model is fixed in the first stage because in the first stage, this model is not there yet, okay? So I want to keep it fixed in space. Then I have an equal DOF that connects the second stage to the first one, and I will apply it later on after the first analysis. Then I have two loads, one vertical load for the first stage on top of the first wall, and then I have a second one. This second one should apply a displacement, should deform both the top wall and the bottom wall because they will be connected in the second stage analysis. And then at this point, what I have a recorder. I first apply the fix it at the base, and then I fix the entire second stage. Okay, so in the first analysis, the second stage will be detached from the first one because the interaction will be added later on. But in order not to have the model singular, I will keep it fixed in space. I run the first analysis, well, I apply the vertical load. I run the first analysis. Once the first analysis is done, I remove the fixity here, which is the fixity that I was using to keep this model fixed in space. I remove it, and then I apply the link, okay? Because now if I remove this one, this object will be detached from the first one and will be singular because it will try to fall down. For this reason, I apply the link in the middle, and thanks to the incremental feature of the constraint, this link will not attach the displacement together, but will only constrain the incremental part of the displacement to move, okay? And finally, I apply a vertical load on top, and I run the second analysis, okay? So I bring this back, before running the analysis, I bring this back to the initial position, and I remesh it. And now I try to run the analysis. Let's see what happens. So first stage, second stage, and let's go here. Okay, so let's go back to the first analysis, and let's see what is happening. Okay, so in the first stage, as I told you, this model is like if it was not present, okay? It's just fixed in space. So I'm running the first analysis, and only the first wall is displacing, okay? And it's up to here. Here, the first step is done. In the second stage, I remove the fixity. I apply a vertical load on top, but I link these nodes to this one through equal DOFs. Now, equal DOFs tells you that the degrees of freedom between the master and the slave should be equal. But in this case, it's only applied to the incremental displacement of the second stage. So as soon as I go into the second stage, you will see that this one starts displacing, but the displacement here and here are not equal. Only the incremental part is equal, okay? So if I keep on going, you will see that the load on top of this wall is affecting the bottom wall, but it seems like there is a gap in between, okay? This is just numerical, it's not a problem. It's just because in the second stage, I'm looking at the incremental deformation due to the first one. So it's very easy to handle in this way. You can have multiple stages. The only thing that is not is not really nice to see is to have this gap here. But in STKO, it's very easy to do what the initial state analysis does in post-processing. So if you look at the database here, I have only displacement and reaction forces that I recorded from OpenSees. But in STKO, if you have seen the webinar about the Python API, you can write a very simple script that gets the document from the application, tries to obtain the database with ED equal to 1, which is this one. From the database, I can get two results. So what I want to get is the first one, which is the nodal result displacement at a fixed time. So in STKO, when you request a nodal result like this, you are telling, okay, I want to have the displacement which varies at every time step. But if you apply this extra keyword, so time is equal to something, and in this case, it is equal to the end of stage 1, it means that I want to get the displacement, but not in any time of the analysis, but at a fixed time in the analysis, more specifically at the end of the first stage. And I call it U1. Then I get U, which is equal to the displacement at any time step minus the initial displacement at the end of the first stage, okay? Then I will print it, I will give it a custom name called delta displacement stage 2, and I give it custom component labels, which is delta UX, delta UI, delta UZ, and I add it back to the database. If you have watched the webinar about Python API, you know that this one is called the virtual result because it's not actually doing this operation. It's just virtual. So it stores the operation to be done. And at runtime, STKO will compute this operation for every node. So it will not increase the size of the database. It will not do anything while you run the script. Okay? It will just compute this value minus this value for each node just when you do the plot. Okay? So if I run this one, you will see that now I have a new result here. And it has been immediate, so it didn't do any calculation, because as I told you, it's not really creating the result. The result will be created when I try to plot it. So instead of looking at the displacement, I want to look at the delta displacement, and also the deformation should be the delta displacement, okay? Now, if I start from stage 2, and I try to run this one here, you will see that now I see the displacement only at stage 2. And you will see that now they are connected, because actually the multi-point constraint is connecting only the incremental part of the displacement, while the stress is basically the same. Section force, and here. So you will see now that if I apply displacement equal to 0, and if I go back, you will see that the stresses at the beginning are only on the first model, first part of the stage, and then also on the top. Okay. So this one is a very easy way for doing construction stage analysis without relying on the initial state analysis wrapper. Okay. So in this way, you can do multiple stage of analysis, not only two. Okay. And yes, with this one, I finished this webinar. And now if you have any question, we have some more minutes. But the idea with this webinar is that, because I've seen that many users, when they have problems with instabilities with their model, most of the times is due to constraints. Sometimes because they forget to assign certain constraints, so the model is singular. But many other times is that they applied all the constraints correctly, but the constraint handler is not able to apply them. And the problem with the transformation is that in OpenSees, it does not warn you about the fact that one constraint has not been applied. Okay, so it simply skips that constraints, and you will realize it if you look at the results and you see that some part of your model is floating, and you can realize that. So typically what I did before was to do an eigenvalue analysis, and in that way you can see if there is a very huge period or directly an instability. Oh, and just remember from version 3.7, because if you try to use this code with a previous version, it will not work. It will tell you just that the automatic constraint handler is not available in OpenSees. So just download or compile the latest version. Okay, so if there are no more questions, I want to thank you for taking part in this webinar. And there will be our next webinar in April. We will send you, we will create a post when we schedule the date, and it will be on steel connections. So how to model steel connections in STKO and OpenSees. So once again, thank you everyone, and see you to our next webinar.